Okay, thank you. Thank you for inviting me. This is a project that's funded at Bristol by BHP, part of an initiative that's been running for a few years now, and it's a collaboration with Moscow State University. And the title really reflects the fact that our view of magmatic systems is different now to what it was in the 1970s when models of porphyry copper formation were first really developed. And the question is, have those changes in our understanding of magmatic systems changed the way we look at porphyry copper mineralization? And I'd like to suggest that they do. So if you're thinking, well, why? How have things changed since 1974? I think the main change is that we don't really see magmatic systems as dominated by this large liquid-filled magma chamber in which all differentiation and degassing occur, situated a few kilometers beneath a volcano. We see magmatism and, in fact, mineralization as the end product of a process that actually traverses the entire crust, probably from the moho right up to the depth of just a few kilometers. And the system is not dominantly liquid. It's actually mostly crystals. It's in a mushy state, and in that mush, melts and crystals and indeed gases move independently of each other. Obviously there are magma chambers, volcanoes erupt. That's testament to some body of melt at shallow depth, but that is not the normal state of a magmatic system. And that's the reason that geophysics has been signally poor at finding large magma chambers, because they exist for only very brief periods of time. So in a different world, a non-magma chamber world, we've moved from something like this to this transcrustal mush, where what comes out the top, be it a volcano or an ore deposit, is the integrated consequence of a process operating over 30 degrees or so. The transcrustal mush is fed at the bottom in an arc setting by a hydrous arc basalt with a few % water, derived from the mantle wedge. And as it passes up through the system, it crystallizes and differentiates. It releases volatiles, depending on the pressure at which the degassing occurs. And the melts and the volatiles move upwards, and I shall suggest that they actually recombine somewhere up here, because in a transcrustal system, whatever you release down here ends up coming out the top somehow or other. So in terms of making a porphyry system, you have an input. This could be the arc basalt with not an awful lot of copper. In fact, basalts around the world have about 100, maybe 80 to 100 ppm. An amount of sulfur that we could debate, but 1,000 is a good number. In some arc basalts, that could be as high as 3,000. An amount of chlorine, that's a fairly typical number, 1,500 ppm. And water content, 4 is a typical number, but arc basalts can go from being quite dry to really quite a bit wetter than that. And the sulfur to copper ratio, this weight ratio, is about 10. Right at the top of the system, we sample fluids as these intermediate ID density fluid inclusions in porphyry systems. There are quite a few data out there that we can draw on. Cyril showed an average from a compilation. This is just data from Bingham. And here, the fluid, the supposed mineralizing fluid, has a couple of % SO2. It's fairly salty. It has about half a weight % of copper. And it has a sulfur to copper ratio, not very well constrained, because sulfur is very hard to measure in fluid inclusions, of around about 2. The thing we're trying to use that fluid to make this deposit, and this deposit over here is something with 80 megatons of copper. This is a very poorly known number, the amount of sulfur in a deposit. The ratio for this particular deposit, these are proprietary values, I can't reveal my sources, but the ratio of sulfur to copper here is round about 8. It's quite a lot bigger than the sulfur to copper ratio we'd need to make chalcopyrite, because the sulfur in a porphyry copper deposit isn't just chalcopyrite. Porphyries contain pyrite and anhydrite. and all sorts of lower temperature alteration minerals like alunite. So just matching the sulfur to copper ratio of your main ore mineral is not quite enough. So we seem to need to make something with a bigger sulfur to copper ratio than we actually have in the fluids, but something closer to what we have in the basalts that are feeding the system at the bottom. So we can imagine here we have an input, we have some sort of a process, it's magmatic differentiation, we have an output that's a fluid, we have some sort of a process that turns that into an ore deposit. So when we came into this, we're in the group in Bristol with petrologists and volcanologists. We didn't know our digunite from our bornite, which I think is a fairly cardinal sin in the world of economic geology. We're getting better, but so this is a purely petrological perspective on the problem. So crustal differentiation, we've heard quite a lot this morning already that there doesn't seem to be a magic bullet in terms of copper endowment. We don't see anywhere in the world super copper-rich magmas. You start at around about 100 ppm, this would be a magnesian magma out of the mantle, and it's just kind of downhill from then on. There's maybe a little bit of an uphill, but by the time you get to the silica-rich magmas that are mostly associated with porphyries, you don't have much copper left, 50 ppm on a good day. And that's widely attributed, these trends here, this is from a paper by Cynthia Lee and others, these trends show the increase in copper as a moderately incompatible element, then being arrested by a decrease, and that's the saturation in sulfide. And for a long time, the idea was that we needed to somehow circumvent sulfide saturation during magmatic differentiation to prevent this catastrophe that drops the copper content of the evolving melt. So here we are, primary arc basalts, about 100 ppm. The D, copper is not perfectly incompatible. Intersilicate minerals, it has a D of about 0.1 or 0.2. Sulfide minerals sequester copper quite strongly, partition coefficients of around 1,000 or so, so quite a strong effect. You see the copper goes up and then comes down. This is different FO2s here. The more oxidizing you are, the more you can hold off sulfide saturation. The key thing here is that evolved melts don't have very much copper. So without doing any elaborate research, you can see that the challenge in making a porphyry copper deposit is taking some large volume of magma that doesn't have an awful lot of copper and concentrating it into a small volume. And to do that, we need a very favorable partition situation. Let me just talk first about sulfide saturation. Is it a catastrophe? Is that the end of the story? I think the point is you can't avoid sulfide saturation. Magmas will saturate in sulfide at any reasonable redox condition in the earth. So these are some experiments. A PhD student of ours in Bristol, Vlad Machushkin, did some very nice experiments, and I think the important take-home message is here. This is the ratio of sulfur that is in the oxidized state in the melt, S6+, divided by the total amount of sulfur. And so when you're up here, it's all sulfate, and when you're down here, it's all sulfide. And what Vlad showed is that this transition, it's very steep because it's an 8-electron transition from 6+ to 2-. This transition migrates from higher pressures to lower pressures across about 2 or 3 log units. What that means is that sulfides are stable even at quite high FO2s in the deep crust. So unless your magma is way up here, I don't think anyone would suggest arc magmas are at nickel-nickel oxide plus 4 log units. You can't avoid sulfide saturation. So if we're trying to come up with models of arc differentiation, we're going to have to deal with sulfide saturation. You can't get around it unless you're super oxidized, or there's one obvious other way to avoid sulfide saturation that you've all figured is avoid sulfur altogether, then we don't have any sulfide saturation. And one way to avoid sulfur, or reduce the amount of sulfur in the system, is obviously to this is reduce the content rather than reduce the valence state, is to have a lot of water, and then you can degas the sulfur. And so if we want to understand how high water contents can strip some of the sulfur out of the system, we need to understand the partitioning of volatiles, sulfur in particular, between fluids and magmas. So that's the take-home message here, this steady shift of the sulfide to sulfate transition, favouring the sulfate at lower pressures. So, if we want to understand the fate of sulfur and the other really important volatile component, chlorine, we need to know something about the partitioning behavior. Now, there are two ways of approaching understanding the partitioning behavior. We can look at volcanic rocks, or we could look at experiments. If you look at volcanic rocks, what they tell you is that evolved, relatively degassed magmas still have quite a lot of chlorine, but they've lost most of their sulfur. So the message from volcanology is that sulfur and chlorine are fractionated from each other. They degas at different times, such that chlorine is hanging in there till the bitter end, whereas sulfur has long since gone. That would suggest that the sulfur partition coefficient is rather higher into the fluid than it is for chlorine. Here are some experiments that we did. There are two sets of experiments. These are from our lab on Stromboli basalt, and these are from Hanover on an andesite under oxidized conditions. And they just show the same story. This is decreasing pressure here. So we start with a magma somewhere over here that's got quite a lot of volatiles, water and CO2 and so on. And what you see is that as the pressure drops, sulfur increases ever so slightly and then takes a dive around about 200 MPa. Sulfur is degassing very efficiently at 200 MPa or so, whereas the chlorine content flatlines right down to 25 MPa. So chlorine is degassing in a very different way to sulfur, and that's consistent with volcanic rocks. The partitioning data, on the other hand, are a little bit less clear on this point. This is the Gospel according to Shinohara. This is a classic paper in 1989, and what that paper says is that chlorine loves going into the fluid, or the vapor, V here, and its love for the fluid increases at higher pressure. So degassing at high pressure drives all the chlorine out and into the fluid, which is a bit hard to reconcile with these data. Conversely, here are some data on the sulfur partitioning, and those show an incredibly strong dependence on the composition of the melt. By and large, these numbers, this is for a haplogranite, are rather higher, or at least as high as these numbers. These data are completely inconsistent with these results. Now, Brian Tatich has been doing some great experiments on chlorine partitioning, and he'll present those in the next talk, so I won't dwell on that now. But part of the aim there is to try and reconcile the partitioning data with the observations. There are a lot of problems with these data, I should say. The really, really important component in magmatic systems, the one that is going to enable you to concentrate the copper from a relatively modest magma into a world-class ore deposit, is chlorine. Copper and chlorine complex in the fluid, and the more chlorine you've got in the fluid, the more copper you can carry in that fluid. So that behavior of chlorine from the last slide is critical to forming ore deposits. We want to be in a regime where the chlorine content of the fluid is maximized. That is to say, we want to be in a regime where the D-chlorine fluid over melt is high. This is something Brian and I published earlier this year. This is the partition coefficient of copper between a fluid and a melt. And this is a logarithmic scale. This is how much chlorine, or this is the salinity of the fluid. And you can see there's a very, very steep increase. It's non-linear because of the complexes that form. They're not simple copper chloride complexes. Salty fluids, big Ds. So what's really important is to understand when are those fluids going to be very, very salty, because those are the conditions under which your fluid can sequester, scavenge, what have you, most of the copper that's in the melt. And we see these numbers are really quite big, 100, 200, 300 here. Now, if I take my modest 50 ppm copper and I multiply it by 300, we're sort of in business now. So we want to make sure that we identify that part in the differentiation cycle where the fluids are salty. So we've seen this morning a number of different differentiation models, and this one is a bit similar to the one that Massimo showed or Cyril showed. But basically we have some things we'd like to model, some important parameters. We have some constraints on those parameters, and we have controls on those parameters. And I won't belabor these, but some things, for example, the sulphide solubility would depend on the FO2, the temperature, the pressure, and because John Mavrogenis is here, the iron content of the magma. And the sulfur partitioning would depend on the temperature, the FO2, and the melt composition, and so on and so forth. And the thing is, it's very hard to know. We've got quite good constraints on these parameters, but it's a little bit hard to know how we're going to vary them all independently or together. That's why Cyril does the Monte Carlo, which is a very elegant approach. I'm going to show you a slightly different approach where I'm just going to adopt some scenarios which would be in the subset. There would be a subset of all the ones that Cyril has explored. I haven't included CO2 in here. CO2 is a really important magmatic volatile, obviously, and I think the CO2 content of arc magmas is a little bit higher than has previously been recognized, and CO2 may play a really important role in transporting or not transporting metals and driving their precipitation. So here is a scenario. This is scenario A, and in this scenario we put some basalt in the bottom, and that's the basalt with its water and its sulfur and its chlorine and its copper and so on. And then we differentiate it somewhere in the mid-crust, and we produce about 50% of a melt, which has these characteristics, and we dump out some minerals. It's a bit wet, so there's no plagioclase here. And then we move that andesite up to a lower pressure, so we're now about 10 or 11 kilometers, and we dump out some minerals. Now we've got copious plagioclase, and we produce a melt that's ever wetter. And we're starting to saturate in sulphide here. That's that little yellow bar, and then we allow this magma at this depth to rise up, and now to a very shallow level, and to solidify pretty much completely, or 90%, leaving this residual melt that might be a little porphyry dike and some granite pluton. At this stage, not only have we saturated with sulphide, we've saturated with fluids, and they come off in these little bubbles here, and this is the composition of the fluid, and you can see this early fluid has modest salinity, and this later fluid has higher salinity, and I'm using, for the chlorine partitioning, values that Brian's going to present in the next talk. So I identify a deep fluid and a shallow fluid. The deep fluid has modest NaCl, quite a lot of sulfur, and it's carrying some copper in scenario A, and the shallow fluid is much more salty, and it has somewhat lower SO2 but higher copper. So we can vary some of these parameters. We could vary, say, what we put in at the bottom, or how deep we did the first stage, or to what extent we ran the first stage. We could vary the amount of water in here, and so on and so forth. I could do it all in a big Monte Carlo simulation. I'll just show you 8 ways of skinning this particular cat, and then we'll see which method is most useful. So you don't have to remember all the different scenarios. That was A. But there are variations in water, sulfur, and chlorine. Really just focus on F here. F's the very wet scenario, 6% water in the basalt coming into the base of the system. And it has a deep, an intermediate, and a shallow differentiation depth. So it's a bit like the last scenario, but it's just a bit wetter. And then what we do is I take all the parameters that I think we know reasonably well, and I guess the ones that I don't think we know reasonably well, and we create a model, and we look at how the deeper and the shallower fluid change in composition for these different scenarios. So here are the scenarios, and F was the one I wanted you to focus on. This is the composition of the fluid here. So this is the copper content in parts per million, and this is the SO2 content, sorry, in weight percent, I should have said. This is the SO2 content in weight percent, and at the top here is NaCl. And these are the different scenarios, and the first thing is, it doesn't really matter how I actually do the, how I set up the model. My shallow fluid always has about the same composition, although it's a logarithmic plot, of course. Those intermediate density fluid inclusions from Bingham are shown as these bands. So the orange band should be compared to the orange dots, and the grey band to the grey dots, and the green band to the green dots. So pretty much all those scenarios produce a shallow fluid that is a bit similar to the intermediate density ore-forming fluids that we see at Bingham. They're a little bit lower. These are a little bit lower in copper. This is despite the fact that all of these scenarios saturate in sulfides in the crust. So the point about sulfide saturation is it's inevitable, but it's not a catastrophe, largely because we've got chlorine waiting in the wings with its incredible copper scavenging power. There are also some interesting features in the way in which decompression affects sulfide stability, which was apparent in those Machushkin data. We won't go into those. I've put at the bottom a sort of open question: is sulfur over copper, is that ratio sufficient to generate a porphyry copper deposit? I think that's a discussion that's going to rage for a long time, because we don't have very good estimates of the sulfur content of big porphyry copper deposits. So some people will tell you these fluids are absolutely fine, they've got everything you could ever need, and other people, like me, will tell you they're not enough sulfur in there. This is the shallow fluid. Let's now look at both fluids, the deeper fluid that's coming off from the mid-crust and the shallow fluid, the one that's coming off from the shallow crust. Here are the scenarios again, A, B, C, and so on. I've now plotted the extraction efficiency. This is a very simple parameter. This is basically how much you get out the top in fluid compared to how much you put in the bottom as magma. So 100% is I'm taking all that copper out and it's coming out the top of the system, and 0 is it's all getting locked up in sulfides in the deep crust. So we want a big number on this plot. Here the different scenarios are rather different, and the key point here is F, the wet one. There's the shallow fluid here, but the deep fluid carries rather a lot of copper as well. So if we add the shallow and the deep fluid together, we're achieving a phenomenal extraction efficiency. So what we've learned from that is what we've heard several times this morning. We need wet magmas to differentiate deep. Then you get 2 bites of the cherry. You get deeper fluids that are quite voluminous but carry quite a lot of copper, because the chlorine allows some complexation, and a shallow fluid. If we go to the drier variants, look at this one here, H. That was a dry fella. The deep fluid down here carries no copper whatsoever, because it didn't degas deep because it was too dry, and the red triangle and obviously the green circle are superimposed, and the extraction efficiency is low. So again, we just need large quantities of fluid to make this process efficient. The 4% here, I ran quite a few scenarios. Needless to say, chlorine-rich is more efficient, and chlorine-rich could be start with more chlorine or just have a bigger chlorine partition coefficient. And that's obviously the motivation for what Brian's been doing. Getting the fluid out as a function of the salinity isn't the end of the story. Salinity is even better than that, because when the phases separate, when that single phase, supercritical fluid, the intermediate density fluid phase separates into a brine or a hypersaline liquid and a low salinity vapor, the copper still follows the chlorine into the brine. And this is a nice plot again from the same work that Brian did. This is the copper partition coefficient versus the chlorine partition coefficient. So at any point we push brine over here and vapor is over the other way, and there's roughly a 1-to-1 correspondence. So if we have a 100-fold enrichment in the brine relative to the vapor, we get a further 100-fold enrichment in the copper. So another important twist here is that not only do we take the intermediate density fluid out with its copper and salt, we actually phase separate that at lower pressure, and we get a brine that further sucks up that copper. And this is a very important process, I think, in forming ore deposits. So there we are. We put in the single-phase fluid, and then we form a brine that is ever enriched in copper. And so this is the schematic, really. This is pressure here. This is one of these odd scales that's sort of logarithmic up to here and then linear. I have no idea why they plot them like that. But anyway, these are this is the solvus. This is brine here, and this is vapor over here. And as you come up, so we're coming up, so this is higher pressure. As we decompress, we cross the solvus, and depending on the temperature, we separate out a vapor that has low salinity and a brine that has high salinity, and then we can work out the proportion of copper that goes in here versus here. It's just some very simple algebra. We know that the copper partition coefficient is just the ratio of salinities of that to that, and then there's a weight fraction. You can't use a tie line on a log to linear scale, but you get the idea. You can work out the proportion of the brine and the proportion of the vapor. The thing is, the brine occupies quite a small volume, so it really sucks up the copper, but doesn't take up very much volume. The rest of the steam just leaves the system and doesn't take very much with it. So let's now look. I'll spend the next, how many minutes? The next 14 and a half minutes on what happens to these fluids. What does this look like in my transcrustal mush when it gets to shallow level? So we need to do a little bit of modelling here. We've got a supercritical intermediate density fluid. It's rising up. It's experiencing some heat loss, clear decompression. It wants to phase separate into a hypersaline liquid, a brine, and a vapor. And it's doing so through a porous medium, rock, above a hot heat source, a magma body. And what we've done, this is where the Russians come in. We've taken a cylindrical domain, and the cylindrical domain has a finite permeability. It has a relationship between depth and porosity and depth of permeability. We'll just focus on this yellow line for the moment, and we have porosity varying downwards, so it's higher at shallow level, this is the porosity, and decreases downwards, and here's the permeability in a logarithmic scale in millidarcies. And to begin with, we just put fluid underneath that cylindrical domain. We release it from a magma body, the shallow fluid that I showed earlier, and we see what happens. And then we do a variant on that. We say, well, actually, we're not just releasing fluid into any old crust, we're releasing fluid into volcanic crust. And what we know about volcanoes is they have conduits that feed eruptions, and those tend to be higher porosity and particularly higher permeability. So the second set of models I'll show you actually introduce into this cylindrical domain the orange tighter cylinder, and that's a conduit. So we'll compare the case where we have uniform permeability that follows that relationship with a case where we have an embedded conduit, just like a real volcano, which has this permeability. And you can see this permeability here is much higher than that. There are other technical aspects to this model that you probably wouldn't be very interested in, but the depth here is 7 kilometers, and the temperature is a fixed temperature at the bottom of 600 degrees. And the simulations are performed using it's an oil reservoir simulator called Muffets. The porosity is quite high at shallow level. You see these porosities up at 10, 20, up to 25%. The porosity of the shallow crust in arc systems is incredibly high. We know that from this is the P-wave decrease. This is under Montserrat. P-wave velocities are very low in the top 5 kilometers of the crust. You can only get them that low by having a lot of pore space. So we've got lots of space in this shallow region to store brine, to store any fluid, in fact, but particularly brine because it's relatively dense. And I should have said these are axisymmetric models, and it's 10 MPa injection pressure. So this is the case when we don't have a conduit. And what this is contoured for is the bulk salinity. So this is very salty, and this is 4% salinity, and this is pure water. We have water in the rock in that cylindrical domain, and we get a sort of a smudge of slightly salty fluid sitting around a depth of about 2 kilometers. We don't get brine separation. We don't have any really salty fluids. We also don't precipitate any halite in this model. The main reason it looks like this is that the flow is relatively slow because it's trying to make its way through a relatively impermeable rock, and it loses a lot of heat. And that heat dissipation really accounts for that structure. This is a bit like the models that Philip Weiss has developed well, he was in Zurich, he's now in Potsdam. There was no conduit. There was a slightly more exotic dynamic permeability in his models, but there was no conduit. Now let's do it with a conduit. With a conduit, you get a rather interesting behavior. The axis of symmetry is the left-hand side of these plots. These are different time slices for this is our reference case. Now we're producing very high salinity lenses that are roughly annular in form. They're actually annular with a slightly, I don't know how to describe it really. It's a bit like a sort of it's a shell with a hollow center, like a donut that's been deformed. And over time, that shell at about 1 kilometer becomes slightly broader and it becomes sealed off with a cap of halite. So we're actually forming a very high salinity brine lens. The point about that brine lens is it's high salinity, therefore it's high copper. This is a mechanism to concentrate copper in a lens at about a depth where many, not all, but many porphyry systems are formed. Here are the isotherms. Here's the fluid velocity. If you're looking, you can see convection in the country rock. So this is a mechanism for forming brine lenses, concentrating our copper in discrete volumes around about the volcanic conduit at a depth of about 1 or 2 kilometers. This is a parametric analysis. You don't need to go through all these plots in detail. Our reference case is shown with the circle. We've varied the radius of the conduit, the temperature of the incoming fluid, the permeability of the matrix, and the salinity of the input fluid. The main point here is we need to have a lot of heat in the gas that comes in. We need to have high temperature magmatic fluids coming in. This is 1100 Kelvin, 1000 Kelvin. For cold fluids, we just don't have enough heat to produce the phase separation and this very valuable halite cap that keeps everything in place. In terms of the longevity of these systems, this is a longer term simulation now. This is time after we stopped degassing. So going from 5 to a million years, 5,000 to a million years. These brines stay in place for a very, very long time. They're capped by halite. They are eroded at the sides by fluid convection in the permeable country rock, but they will live long after the magmatism has stopped. That means that these copper-rich brine lenses are very, very stable, and they would be an ore deposit were it not for the fact they didn't have enough sulfur. And the sulfur content needs to come from elsewhere. That would be our contention. Just to show you that these things are realistic, these are, let's take this one first. This is Fuji. These are magnetotelluric images of the subsurface. There's the summit of the volcano. This is resistivity, low resistivity down here, so high conductivity. Here's a lens just at a depth of a couple of kilometers beneath the summit. This is Tal in the Philippines. Here the low resistivity lens is actually an annulus from here to here, and it sort of wraps around. We've turned the salinities from our model into resistivities using the Simio and Kepler model, and the values here closely match the values here. So most volcanoes are underlain, we think, by a brine lens centered on the conduit, having a radius of about 2 kilometers, a thickness of about 2 kilometers, and sitting at about 2 kilometers depth. So most volcanoes have their copper-rich brine lens potential ore deposit. They're waiting for a shot of sulfur. What I like about the brine lens, with its annular form and its discrete top and discrete bottom, is it does look, I think, very like an ore deposit, which has a top and a bottom. And whether it's an extracted molar or a deformed donut, ore deposits do have tops and bottoms. This is Baja de Alumbrera. What we see here is that we have a top and a bottom, and then we have this increasing concentration of ore in these annular shells that's been cut by later dikes, and I think this resembles quite closely the shape of the brine lens. That is, the salinity matches onto the copper grade. So we just need a shot of sulfur to drive precipitation. Some precipitation will, of course, occur as a result of cooling, there's no doubt about that, but I think we're sulfur deficient in this configuration. Fuji needs a shot of sulfur, it's going to form an ore deposit. And there is an example where this is actually happening today. This is Uturuncu in the Bolivian Altiplano. This is the volcano. These are earthquakes here, and this C3 is this shallow conductor. It's not magma, much too cold. You've got earthquakes in there. It's above the brittle ductile transition. This, I think, is a brine lens, much like we've just modelled. And we can actually get an idea of the size of this deposit based on its volume. If we know the electrical resistivity, we can work out how much brine is there if we know the salinity. So we can roughly calculate the salinity of an estimated brine. If we know the porosity from P-wave velocity reduction, we can work out the volume of contained brine. It's not a big old deposit. It's not bad, though. It's 16 megatons of copper. I think most mining companies would get out of bed for 16 megatons of copper. It's in the process of getting its sulfur shot. So here, if you go to the top of Uturuncu, there's actually a sulfur mine, and Uturuncu is degassing sulfur all the while. And I think that sulfur, when it meets the brine at depths of 2 or 3 kilometers, is producing sulfide precipitation. So that's really just a summary of what I've said. This is how we view porphyry copper deposit formation. This is different to the standard model. I want to emphasize it's different to the standard model, but it isn't 1974 anymore. We have a different understanding of magmatic systems in arcs. So I've got 3 things. This looks like a guide to wealth management, I guess. Generate, accumulate, and flush, or flash. But polybaric differentiation of typical hydrosarc basalts, I think they need to be a bit wetter than normal, but they're not exceptionally copper-rich. But I don't think they need to be wetter, more like 6 rather than 4 weight % water. You can't get around sulfide saturation or forming fluids generated from shallow silicic plutons and significant copper-bearing deep fluids. Both fluids play a role in increasing that extraction efficiency. The fluids are focused through high permeability conduits. We know volcanoes have high permeability conduits, there wouldn't be any dispute there. The ore-forming fluids condense or phase separate to copper-rich brines at low pressures. That's just the phase diagram in H2O and NaCl. The brines accumulate in lenses in porous rock above plutons, and we can see that in active volcanoes, dormant volcanoes. And these brine lenses are stable and relatively long-lived. They are waiting to make an ore deposit, providing they can get a shot of sulfur before they are somehow dissipated by groundwater circulation, or the whole lot is exhumed and they're just eroded away. The flush stage then, this is when you push your deeper SO2, released from deeper in the system, and probably CO2, up through the shallow brine lens. With John Mavrogenis and Brian and others, we did some experiments to simulate this process, and the mineralization and the alteration take place roughly simultaneously. We haven't looked yet at tectonic exhumation and what effect that has on the brine lens stability. So this is a model that we presented a few years ago, presented to, I think, universal, what would be the right word? Laughter. So the idea was that we had a shallow, derision, that was a better word. We had a shallow silicic system that is releasing its shallow fluid, and this is shallow fluid coming off, and it's phase separating above that line to little bubbles of low salinity vapor and little droplets of high salinity fluid or brine, which is where the copper concentrates, but it's in soluble form. And then we suggested that what happened subsequently was that mafic magma deeper in the system would provide sulfur, and that sulfur would interact with the trapped brine to produce sulfide minerals. That's these little yellow rectangles here. I think there are some variants on that. I think we see things a little bit differently now. I think we've thought about it a bit more. I don't think specifically that we need to have this mafic injection here. This could just be the discharge from the much bigger, deeper transcrustal system that is releasing its gas from all levels, CO2, SO2, and so on. So syneruptive mafic magma injection is not required. Transcrustal mushies reunite deep and shallow fluids from the same system. If indeed magmatic systems traverse the whole crust, it's very hard to imagine how the fluids released deep don't meet the magmas that were emplaced shallow. This is more like a lens forming rather than just sitting inside the pluton. This is a lens forming at shallower level. The longevity of that lens is rather an important consideration, given that we need it to be there when the sulfur comes through. And I think we really need better constraints of sulfur over copper of the mineralizing fluid. I'll stop there. There's an ore deposit happening on the remote Pacific island of Amba in Vanuatu. It's, you just drill here for 2.5 kilometers. It's there. Okay. Thank you.
Thanks very much, John. We have a few minutes for some questions. If you want to wait for John to pass you the microphone, Jamie.
Thanks, John. I didn't quite understand the salinity scale on your models, but you've got the brine lens you're generating
Yeah.
is via phase state change, via phase separation. Is
That's
that right?
Yeah.
So when you do that, obviously you're generating your low density gas phase.
Yeah.
When you at Urunka, you've got this sulfur gas coming out the top of the system. Could that just not be part of that gas phase that's actually coming off the brine rather than something that's being kind of bubbled through it from depth?
It could be the counterpart to the brine, but it's got an awful lot of sulfur in it. It's very, very sulfur rich. And we haven't analysed it. So it could be the low salinity counterpart with an awful lot of sulfur.
So I guess the follow-on is how much do we know about the sulfur partitioning between brine and vapour phases? How much experimental constraint is there on that?
Well, that's a very good question, because on the list of things I need to do next, actually, Brian needs to do next. Determine sulfur partitioning between vapours and brines. That's the answer to your question. I hope through the course of Famous we can actually have a go at this. I think that's a big unknown. So the answer to your question, it might be, yes, they are the low salinity counterpart. Or it might be they've got so much sulfur they can't be the low salinity counterpart. Or maybe we could use them to constrain the sulfur that's in the brine. Yeah.
Any other questions? Just want to wait for the microphone.
I don't quite see the need for having your sulfur and copper arrive in separate batches. Why can't you transport them together, or why do you need a separate sulfur source? I mean, it seems how you're going to generate your H2S to precipitate this sulfide minerals from the SO2
By disproportionation, that's what you're thinking.
by hydrolysis of reaction of the SO2 with H2O to make sulfuric acid plus
Yeah,
H2O.
it's S4 plus goes to S6 plus S2 minus.
Yeah.
Hydrolysis, disproportionation, well,
Yeah.
whatever.
So why do you want a separate injection of sulfur?
Oh, the main reason, Bob, for that is that if you look at it, if I was to put a compendium of a collection of all the evolved melt inclusions from volcanoes around the world, they don't contain any sulfur. They've got 50, 20 ppm sulfur. There's a few exceptions, but they contain very low sulfur and they have very high chlorine. So by the time you get to shallow levels, you've lost most of the sulfur. And that's the heart of the problem. And that was shown in those experiments there, where you could see that sulfur degasses very efficiently from about 200, 250 MPa, and chlorine doesn't. And we don't really understand why that is.
Well, presumably, you're degassing over, as the magmas ascend, very hydrous magmas, they begin degassing a dense, water-rich, chlorine-rich fluid at greater depth, but the sulfur could largely be retained in the melt because it doesn't have very high partition coefficient of SO2 into the dense hydrothermal salty fluid that it dissolves initially. So much of this
Bob, the initial fluid is not dense and salty at all.
much of the SO2 degassing could occur during subsequent phases of fluid release from the same batch of magma at shallow depth, where the SO2 has a higher partition coefficient at low pressure from the same magma.
Well, I don't think SO2 has a higher partition coefficient at low pressure, and I don't think the deep fluid is particularly salty. I don't think there's any evidence from volcanic rocks or from experiments to support that. There's the Shinohara experiments that suggest that higher pressures have a higher partition coefficient, but as Brine will show in a couple of minutes, those have not been replicated experimentally. Sulfur degasses before chlorine. And in fact, if you were, well, there are volcano gas experts here. The sulfur to chlorine ratio is actually a very good probe in somewhere like Stromboli of where the magma's degassing, because they're well known to decouple from each other. Sulfur comes off deeper than chlorine. Now, it may be that you can blur the whole thing into some column. I wouldn't dispute that happens, but there is no doubt that sulfur degasses, partitions into the fluid phase at an earlier stage in differentiation, a greater depth than does chlorine. Maybe I can invite Marie to comment on that.
Yeah, I agree with everything you say, but I think the critical thing here is how we think about the fluid phase and how it is held within the magma. And I think these porosity-permeability relationships are critical here. Because the evidence we have from volcanic systems is, we have these big explosive eruptions and we typically see a huge mass of sulfur released into the atmosphere. And, we know from ground deformation and from other kinds of measurements that these magma chambers that are being evacuated are very shallow. So the implication there is that these sulfur-rich fluids, yes, they start to exsolve deep in the crust, but they're actually held by the magma quite effectively, probably in gas-rich caps. So you can have an accumulation of fluids which effectively are an integrated sum of what you've outgassed, through the crustal mush system. So I think it's really critical on how that fluid phase can interact with the mush and how it can escape or whether it's held. And I think that's perhaps where our understanding is lagging. And I think that's critical for your argument.
Yeah, my guess would be that the mineralizing fluid has the same sulfur, copper, and chlorine. Eventually has the same ratio as the stuff you put in the bottom, but you just separate them and then recombine them at shallow level. Because I don't think a good question is why those really big sulfur-emitting eruptions do they produce a lot of chlorine as well, or has that not been looked at?
There are very few measurements, but there is some data for Pinatubo, and that, there is a big burst of chlorine. Oh, yeah. Okay. Well, the thing is with the chlorine partitioning, I'm sure the next talk will show this, that even though the partition coefficient is much lower at low pressures, it's actually the water. It's partitioning into an aqueous fluid phase as the magma ascends. Yeah. So even though the partition coefficients they don't look the right way round. You have weaker partitioning at low pressures than at depth. It's because you have so much water degassing, the actual mass balance works that most of the chlorine comes out at low pressures.
Well, that's the critical thing. It's the D multiplied by the amount. It's the weighted average D. So it's the amount of fluid and the D multiplied by each other. Anyway.
Seems like a good point to move on to our next slot. So just thank you very much again, John.
Thanks.